Yeah, well, I guess these are this is an update on the async sketch. If anyone is remembering, maybe more than a year ago, I did like a rather long sequence of presentations, and this is all before resource types on how async might work. This is like a much shorter and condensed and also simplified update of that sketch, just based on understanding of the last over the last year of like doing resource types and ownership and all that stuff. So this is a hopefully much simpler proposal that still achieves those goals. So I'll start with just trying to what is the problem we want to solve, and I think WASI-HP gives us like a perfect concrete example to like identify the problem and say what we want to fix. Then I'll describe kind of like abstractly what the goal state is, and then give a high-level design summary. Then talk about kind of how we can break this out into some milestones. Then dive into a few more like medium-level design points. And then finally, Joel just recently got a really cool experimental sort of prototype working that you can think of as like the first step towards part of what this is proposing. Like we'll be able to characterize it more precisely later on. But so we'll end up with actually being able to see some kind of working code. So awesome job, Joel. So starting off, let's say before, in the very beginning, and several people's sketches and prototypes they made, WASI-HP could have been so pretty. It could have looked kind of like this. There would be a request resource, and you just construct it, given a nice little list of bytes out of the body. And of course, this is overly simplistic. You'd have a separate resource for a body, but just so it fits on briefly on a slide, you just pass in a list of U8s as the body, and when you consume, you get a list of U8s as the body. And so, same for response. And then the handle function at the bottom, this takes a request and returns a result response. It would be so nice. And it's modular. That's not coupled to any other interface. It's just its own little freestanding thing. It's not dependent on some monolithic core that has to be like kind of like special or magic. It's just its own little HP thing. It's also very composable. So Peter's going to be talking about this later today, but WASM Compose has this upcoming kind of composition language that I'm just showing a little snippet of, just because it's such just a nice concise syntax for like describing composition. So let's say I have two microservices, quote unquote, but they're just components that are targeting WASI-HTTP. I make the first one, I give it a key value store. I guess technically not targeting literally WASI-HTTP, but it's importing KV store and exporting a WASI-HTTP handler. And the next one imports an HTTP handler and exports HTTP handler. So I can just compose them together, just like that. Just link them together. That looks really nice. Kind of this is like a visual representation of what I'm linking together. And this is kind of a little bit. You can think of it as like a non-distributed version of a service mesh, where I'm just taking two microservices and linked them together. It's also, you can think of it as a little like a Unix pipeline and how I'm going to snap them together in composability. But it's fundamentally more expressive than Unix pipeline. We have it's bidirectional. Unix pipelines data flows in one direction from standard in to standard out. Down the line. Well, this gets to go that down and then back up again because we have call return, and also any microservice can call each other 0 to n times, not just once. So it's kind of like, and so you could say like this difference in shift in expressivity is from first order composition of pipelines to higher order composition. And that you could say this is why people do tons of microservices in practice, but not every program is implemented as like Unix pipeline. It's because you actually want this expressivity. And this is what we would have if only WASI-HP could look that simple. You can do these nice, there's like a show of the control flow, calling into one, and you can hop in the other microservice and go back, and hop in again, and return back. So this is a thing that we would be able to do if only WASI-HP looked like that. But then, concurrency. What do we want? What are our requirements here? Well, we got to have streaming bodies. Why? Because they can be really big. We don't want to. Also, we care about latency. We want the first byte. I want to see it before the last byte arrives. And some things, use cases like long polling, like critically depend on this. Next, we want to have multiple outgoing concurrent requests. So I can send multiple HP requests in parallel. And nice to have, because actually various places don't have this at all, is concurrent incoming requests. I want to be able to have multiple requests handled by the same instance, interleaved executing, so we can increase the density of reuse. And naive HTTP can't do any of this. It's that source of beauty was also its undoing. That's why we can't have nice things. And I think this is true for pretty much any WASI API. There's nothing actually HTTP specific about this. If you've got a large list of bytes, you're going to want to stream it. If you import IO operations, you're going to want to be able to issue multiple in parallel or currently. And if you have incoming IO, like triggers, like the HTTP handler, when you get given a request, yeah, you're going to want to be able to have multiple of those executing concurrently. And and if you give a nice composable looking sync function call interface, you won't be concurrent. And so you're going to have to do what we did. So what were we forced to do to be concurrent in preview 2? First of all, we had to split request into 2 for incoming and outgoing, and then response into 2 for incoming and outgoing, returning an input stream and output stream. And then we have this, special magical WASI IO, which defines a resource type pollable. And we have a poll function that, given a list of pollables, says, which one's ready. And then all these different, places of, input streams and output streams transitively will give you one of these pollables. And so you can have lots of different operations in flight that give you pollables. And then once you have lots of things in flight, you can poll, say which one's ready to make progress. And so I won't go into the precise details, but I'm kind of just giving a sketch of, what we did instead. And so, there's a loss of modularity here. Poll has to know about everything. This one function poll has to know all the different kinds of async stuff. It has to know about HTTP. But if we also have, file IO, it has to know about that. If we have sockets, it has to know about that. It's this one pinch point function. So, WASI IO ends up being this kind of like magical monolithic thing. And anyone who's tried to virtualize WASI IO kind of knows this. It kind of just problem forces itself upon you, and you're like, this doesn't feel like that modular, dream I was pitched. You're like, yeah, concurrency, man. So, and what happens, that handler interface gets split into 2. There has to be a different one for incoming that has the signature where you get given a request and an outgoing response, just a simplification of what it really is, and then outgoing where you pass out an outgoing request and you get back as a result an incoming request. Importantly, and this request handling isn't even concurrent in this model. And importantly, they're not the same interface. These are different types, like fundamentally, and you can't just trivially it's not like in some superficial way. So what does this do to our composability? Well, that nice little composition I showed just doesn't work. Why? Because when I try to link them together, microservice 1 exports an incoming handler, microservice 2 imports an outgoing handler, and they're just not the same or trivially adaptable. And so how do you have to compose instead? Well, you have to run each component in a separate thread using host magic powers, because that's just not a thing you can do right now in the component model. And why? Because once a single component calls pull and blocks, well, if they're all sharing a single thread, well, then they're all blocked because there's only one thread and you just blocked it. So if you want them to actually run concurrently, put them in each thread using magic coach powers, and you're like, oh, I had to step outside the component model to compose. So we've lost compositionality. Yeah, and it's not ideal to require threads because we want to certainly allow you to use them, with components, but we don't want to say they're the basis of how we compose when currency is involved. We want to allow but not require threads. So ideally, my ideal world, and actually spoiler alert, I think this is what in preview 3 we'll be able to write, is I just want to take that original interface and just cross out the list and write stream instead. And that's it. That's the WASI I want to write. Now, obviously, real WASI is a little more complicated. There's bodies and there's fields and all these things, but basically that's the fundamental change I want to make. And there's no WASI IO in this picture. There's no monolithic core where everything funnels through, and it goes back to being composable. Now we have the same handler interface, so my 2 microservice E components can just compose. So that's the way I want to write. That's the way I want to standardize and publish. So how does that actually give me the concurrency that are the requirements? So here's the TLDR, and this is just a very brief high-level summary, and then I'll kind of recurse into each of these. So first, we need to, I think, what we're proposing is to add a new async canon opt to canon lift and lower. So canon lift or lower are basically how you go between a component level type and something core wasm can import or export. And we have all these canonical options, like string encoding, where you get to say, how do I want my string to be written into linear memory or one day GC memory, as we were talking about yesterday? Well, to that same place of how do I want it to look precisely, we can add an async option. And async, and I'm going to hand wave here and just say, means reentrancy, which means being able to run new invocations while something's already running. And I'll say more in detail how this actually works. And so as a canon opt, like string encoding, async is not part of the type. It can be uniformly applied to any function type, just like, all the other canon ops. And it can be independently chosen by the caller and callee, because it's, on one side or the other or both of a particular, function call. And it can be independently chosen for each import and export. which is actually going to be useful, as we'll see. And that's exactly kind of what we need to handle all the use cases that we have. Separately and orthogonally from that, then the proposal is to add a future and stream type that can be used in parameters and results of functions. This is what I showed on the previous slide. Consume can return a stream of U8. They allow incremental delivery of values as opposed to passing or receiving parameters and results all at once, which is how they work today. All the parameters get given to you, and then you run, then you produce all the results and they get copied, and the caller gets all the results at once, and then they run. So this future and stream, they're about incremental delivery of parameters and results. And so with the design, we make async totally orthogonal from the use of the future and stream type, where async gives you reentrancy, where future and stream give you incrementalism. And that means you can, for example, synchronously lift a function because you're non-reentrant code, because let's say you're C or Python, and you're just not, the code, this is fundamentally not reentrant, you don't expect to be reentered, but you can still use streams because you want to use streams because you want to not So, and this is what you need for all the languages that aren't inherently async, like, so REST async, JavaScript promises, C# async, these languages, are fine with being reentered, but a lot of other languages, just you can't force this on them. So we want to be able to have these orthogonal concepts. So that's a high-level sketch. Expect there's still questions, so let me go into a little more detail. And then after this detail, I'll show some actual diagrams with call stacks, and we'll see kind of how it works in practice. So let's see how lowering async works. So already we have this concept of canon definitions, which lets you lower a function. So ignoring the async part, this would say, given a component level function f, can you see my, yeah, you can see. Use this memory to, read and write its parameters and results. Use this realloc function if you need to dynamically allocate memory, and give me a new core function f that can be imported by core wasm. So this is already a thing you can write. And the new thing is, additionally, in addition to these other options, I can say async. And when I do that, this core function will be given the fixed type that doesn't even care about the type of f. I give it a pointer to a tuple of parameters and a pointer to a result tuple that will be written into, and I get back a state of the call and an index into an internal table that holds an index to the asynchronous call that may be in progress. So digging into that, the param tuple pointer, result tuple pointer will point to, well, a serialized tuple of whatever the parameters and results are, which is already what we do when you exceed the maximum number of parameters or results that will flatten. And when you have too many of them, we already stick them in memory. Well, we use the same thing here. We're just always putting them in memory, basically, instead of trying to splat them out into different I32s in the results. So that's not a new thing. We're just going to do it always because it's what we want. So once I make this call, it'll return to me without blocking, and it'll tell me what state the call is in. So there's 4 states. The first one is the call hasn't even started yet. Why? And I'll tell why this case is very useful next, but the call hasn't started yet. So therefore, I haven't even read from that parameter tuple. Keep it live. Don't free that memory yet. Keep those parameters available for me. And then wait on this call index to know when they have been, when the call is actually started. 2, the parameters have been lifted, so you can free that tuple, but keep waiting for the results. They're not ready yet. Keep that memory live. We're going to write into it a little later. State 2, the parameters have been lifted. The results have been written into the tuple, so you can use them now, but the call's not done yet. It's still finishing up. It maybe is going to do some billing or some logging or some final stuff. It's not done yet. And 3, the call is totally done. It is released. The memory is freed. The index is gone. And so we're done here. So it's possible for because state is a return value, it's possible that I will make this async call and it will finish. There was, it just finished. There was nothing to block on, so it's already done. So I didn't even do an async call. I didn't allocate a resource. You can return a Rust future that's already ready. So it's possible to go straight to state 3, but it's also possible to go to any of these earlier states. In that case, the call's not done yet. So given this call index, well, how do you wait on it? Well, that gets into lifting. So this is lowering how we call imports. Let's see the other side of this, which is how does our exports get called? That gets into how lifting works. So when we're lifting, we're going the opposite direction. We have a core function of exported by core wasm that we want to lift into a component level function that can be called from the outside. We're going to say, use this memory, use this realloc. That's already what you can say. And the new thing is we can say, I want to lift asynchronously, and here's my callback. So this is a second function. So I have 2 functions I'm giving here, the callee and then this extra callback function. I'll explain what it means shortly. So that's what's new. And then the result of this will be a component level function. And let's just say whatever, I give it some type string to string. So when I lift, this core function must have the fixed type. It takes nothing, and it returns whether it's done or whether it wants to keep going. And here's a closure pointer that will be passed to my callback. So returning done equals 0 means wait for something to happen and then call my callback given this closure pointer, which is like the void pointer sort of low-level Unixy kind of callbacky pattern. So that's if I'm not done. If I am done, then the call is done. There's nothing async that needs to happen. I didn't end up blocking. The callee, before returning done, must have, and this is enforced by a trap, have called two built-ins. So while it's running, it needs to call two different things to be done. One, it has to start. And when it starts, it gets its parameters. So when I call start, I pass nothing. And then we use the normal canonical ABI to copy the parameters into my memory. So this lets me wait until I'm ready to receive the parameters. And that's when I call can and start. And if I don't call start and I return, what I'm saying is, hey, I can't even receive this stuff. I'm already backed up. This is back pressure, right? Because the allocation of like a list of U8 pushes memory into my space. If I have a slow other side of a stream, I need to say, hey, don't do it yet. I'm going to So I need to be able to exert back pressure before the call even starts. This is useful for this reason, but there's even more useful for the next reason I'll get to later. But critical thing not present in the initial sketch is back pressure before a call even starts. So that's task start. Task return is the opposite. It's when I go the opposite direction. I give you a pointer or the canonical ABI representation of my return values, and this copies it into the caller's memory. So I can task return. And because when we have task return, we don't need this post return anymore when I'm doing async stuff, because as soon as task return is done, I'm post return. I have returned my values. I can keep running, and I can keep waiting and doing all the other stuff. So these are the two things I need to do before my call is done. To start it, which gives me the parameters, and I have to return, which lets me pass out the results, all before my async, and I can just keep running after the return to finish up what I want to do. So that's that. So now let's say I do have to wait. I return done equals 0 because I need to wait for something to happen. I need to wait for progress. This callback gets called with the closure I asked, and then an event, which is like a kind of a union discriminants, and then these two I32s, which are just like, you can think of as like, two raw bytes that are interpreted by what the event is. So this is like a flattened union here. And then I get to say after this callback, am I done now or do I keep going, waiting on the callback over and over? So this is kind of our event loop system local to this component. So if I return done, same rules. I must have called start and return, or task start and task return by the time I'm done. And the event says what happens and how to interpret the payloads. And initially I'll add more cases, but the initial one is event 0. I'm just making up the numbers here, but let's say event 0 says I made progress on a call, and payload 1 contains the new call state. I guess payload 2 would be the call index. But what this is saying is, hey, one of these subcalls you've made by calling in imports has made progress. This is the new state the call is in. So if I called an async imports and I was waiting for it to return its results and the state is now 2, I know, oh, the results are ready for me. I can, proceed on that import. So this is how I wait on all the import calls I've made, is I wait to hear progress on one of those import calls. So that's, a lot of abstract kind of rules. Let me talk through an actual call stack and progress. So let's say we've got these two components linked together, and we're going to do the case where they're both async on both sides. And we're going to actually walk through when one side's async and the other side's async. So we'll start with the both async case. So, the x-axis is over time, and the y-axis is the native call stack, what's actually happening in the VM. So, we call in to c2.handle. This is let's say it's washp. So this is the handle function of washp. And that starts this task, gets its parameters. Then it calls into C1's handle function. It's C1 starts its task, gets its parameters from C2. That transfers ownership of that request handle. And now C2 wants to call the key value store gets, which ultimately, let's say, is implemented in the host. And this is where we would block. We're okay, we're going to have to do a network call here. So this is where we would block. If this was a synchronous call, we would just block here and not return. But instead, we will return because C1 lowered with async. It will say, okay, I've created a call at index 0 and it's in state 1. I've read the parameters, but I don't have the results yet. And this will return, and C1 will say, okay, well, I can't make any more progress, so I'm going to return, I'm not done, and I'm going to return a closure pointer, some arbitrary number I picked, pointer to memory. So now 2 gets control flow, C2 gets control flow, and it says, okay, a call was created in C2's tasks index space. It has index 0, and it's in state 1, which is the parameters have been read. And now C2 gets to keep running, and it says, okay, I can't make any more progress, so I'm not done, and here's my closure pointer. So then time passes, that host.get, that network request finishes, and so the host now calls back and says, okay, C1, we've made progress. Here's your closure pointer back. Call index 0 made progress. Now it's state 3. We've got our results ready. You can now have the results from the gets. You can keep running. So C1 computes its results. It does a task return to pass out its results. And then it returns, okay, I'm done. So it returns to the host. Now the host says, okay, well, I know who is waiting on that. It's C2. So it calls C2's callback and says, all right, here's your closure pointer back. Call index 0 made progress. And now it's at state 3 of your turn value. Task C2 returns its task results, which is they handle to a response. And that returns to the host. And now we're done. So that's the whole call sequence. So in general, I've showed just one callback invocation each, but they can be interleaved over multiple things. If we're streaming, we're going to be if C1 is, we're streaming from the KV store into C1 and C1's transforming that and passing that into C2, there'll be lots of interleaved callbacks between C1 and C2, just like an event loop, as if they were all part of if they're all written in JavaScript using a shared event loop. Yeah, but they now have different languages and we're interleaving them with an event loop because they're both async and using this callback ABI. So in general, they can be interleaved. And the other important thing is that C2, after it's made this first call into C1, it can call back again, right? C2 can make a new export call into C1 and do another concurrent handle, and it'll just be more callbacks with different closure values that are interleaved. So this is kind of like a very low-level ABI on which you could build, Rust promises, Rust the futures and JavaScript promises, etc. So that's the, in some sense, easy case when they're both async. Let's talk about the mixed ones because these need to compose. So let's start with the easier of the two cases when sync calls async. So sync means we've lowered synchronously and the callee is lifted asynchronously. So we call into C2 handle. It's a big old synchronous function call. It's going to call into C1. And so I'm going to show something I left implicit in the previous one, which we always call through an adapter, right? That's the case of today. When you call between two components, you go through this fused adapter, which sees both sides and kind of says, I know what both sides want to do, so I'm going to do that thing efficiently. So it sees I'm async calling, I'm a sync caller calling an async callee. So I'm going to do a thing. So I'm going to call C1's handle function. It's going to start the task. It's going to call the get. It would block. So it returns to C1 just like before, which returns, okay, I'm not done. Here's my closure. But because this adapter knows C2 is a synchronous caller, it's going to say, well, I need to spin the event loop right here. So it's going to wait right here. And eventually we'll finish, which will call back into the callback, said, okay, we made progress. It's done. C1 will return its results, say, I'm done. And now the adapter says, okay, well, we're done. The caller can now synchronously return its value. And so C2 returns. So that's kind of what you would hope. Nested event loop, basically. And so that case works. That's the easier one. The harder one's next one when we invert this. Let's talk about the fun case, async calls sync. So we call into C2, it's async. It starts its task. It now calls into C1. And it's, now we have this adapter that knows that the caller is async and the callee is sync. So now we call into C1, which is a synchronous function. It calls the host get, which it expects to execute synchronously. We get to the point where we would block. And at this point in time, we suspend the fiber. So the fundamental functionality here is we're going to suspend this stack and return back to the adapter so that the adapter can return back to C2. Because C2 doesn't want to block. C2 is saying, if you would block, return control flow to me so I can make progress, so I can issue other IO. So the fact that C1 is synchronous shouldn't kind of break the asyncness of C2. If it did, it wouldn't be very, C2 wouldn't be actually being lower, it wouldn't be lowering async. So we need to return control flow back to C2. C1 has, is on the stack. So what do we have to do? We have to have suspend that stack. And this is that same feature of stack switching that we're talking about core WASM and the same feature that's implemented in JavaScript promise integration in browsers. This is that kind of switch the stack operation. That's like the kind of fundamental low-level primitive that we're kind of adding here. So we suspend this stack so that we can return to this adapter, which now returns control flow normally back to C2. Says, okay, there's a call created, it's not done yet. C2 can keep making progress. So we're going to talk about the harder case next, but let's talk about the easy case here where C2 just says, all right, I'm done. I'm going to return, I'm going to wait, and then time passes, the host call finishes, so we resume the stack now. Now, the host doesn't literally have to suspend itself. It could be doing async stuff, but it's logically, from the perspective of C1, suspending and now resuming when it's done. So it finishes, the host has its result, it returns that result to C1, C1 gets to keep running, and now it says, okay, I'm done, so it returns. And now that C1 is done, the host knows I can resume C2 and say, okay, this call has made progress, the results are ready, and now C2 gets to run and finish and result. So that's the kind of the easy case. The hard case you have to now ask is, what happens if while C1 is suspended, C2 tries to re-enter it? Because it can. C2 doesn't know that C1 is synchronous. From its perspective, it just called a function, is asynchronously, it's suspended, got control, so C1 can call it again. Or so C2 can call C1 again. Furthermore, C1 can be imported by lots of different components, and one of those other components has no idea that C2 called C1 and C1 suspended. C3 now wants to call into C1 because that's what you're normally allowed to do. So we have to handle this case, and we don't want to trap. So what do we do? So I just shifted the same diagram over. So we get to the point where we called into C1, it suspended its stack, we return to C2, and now C2 wants to call back into C1, let's say. And we call into that same fused adapter. The fused adapter knows both sides and says, I see that C1 is suspended. I can't re-enter it now, it will blow it up. So instead what I'm gonna do is exert back pressure. Back pressure was the key ingredient. It's before making a call, there can be back pressure. So what we return is that, there's a call was created, it hasn't even started yet. Your parameters haven't even been read yet, right? So that the parameters are still sitting in C2's memory, and the call hasn't started yet, but it does have an index to a call that represents the async call it started. So now C2 says, okay, I can't make progress, I'm gonna return. I have 2 outstanding calls now. And so time passes. The original host call finishes, we resume the host call, it returns to C1. C1 is now resumed, it has not been re-entered, it just synchronous call returned. It now says I'm done with the results. And now we have 2 choices. One of the 2 possible things that can happen. One thing that could happen is the host knows, C2's waiting on a second call to C1. It has that knowledge because this fused adapter here, when it did this suspension, it kind of added a little, it recorded that state. So we said, okay, the first call's done now. Let's make the second call into C1. Let's sequentialize it. It's as if there was a lock here. So now we make a second call, and this one calls in the host, this one blocks, and we turn back. C2 now can receive the notification of the completion of this first task. So this first task finished, returned its results. So we can now deliver the results from this task to C2, even though the second task just got started. And importantly, this delivery of this event to C2 could be swapped around with this starting of the C1 thing. You get better parallelism if you start this one first. So a scheduler would probably want to do it first, but it could technically do either. It's both valid interleavings. Anyway, C2 now gets to run, it gets to receive its results. Time passes, the second host call finishes, so it resumes, it returns to C1, that says it's done now, and now C2 gets a second call back saying the second subtask is finished, it's made progress now, and now it's done. Well, there's a lot more design lower levels, but I'm glad I got through this thing. I would like to switch gears to Joel now, because Joel did a really cool thing, and I'd like to let Joel talk about that.
All right, so hi everybody. My name's Joel. Thank you very much, Luke, for teeing this up. So I posted this in the WASI in the Bytecode Alliance Zulip yesterday or the day before. But this is a project I've been working on for the past week and a half and actually thinking about for the past couple of months because I, like Luke, am very excited about async and want to see what the developer experience in particular might look like. I don't know about you, but looking at these diagrams of control flow can be very abstract, and understanding how all these can and built-ins fit together can be sort of difficult to put together and connect with sort of real-world problems that developers might be solving. And Luke got into that a little bit with some of the HTTP examples, but I wanted to kind of take this opportunity to both introduce this project that I've been working on, and also show some examples that work today, that you can actually run today, and hopefully will give you a taste of what this would look like in Rust, and if you squint, maybe similarly to any language that has sort of this async await paradigm, such as JavaScript, Python's async IO, .NET, and so on. So I'll at some point I'll put a link into the chat, but this is it's called I sync, you sync, we all sync for async. We can come up with a more boring name if we make this more efficient or more official at some point, but I thought that was kind of fun. And so essentially there's two goals here. One is to provide real world implementation feedback on this whole async design and implementation project that we're embarking on. And the other is to provide a sort of polyfill that developers can play with today and going forward while they're waiting for preview 3 and the real async. And in short, we're trying to create that developer experience while minimizing the disruption and to the ecosystem in terms of tools, and adding all these canon ops and lifting and lowering, which of course is going to touch a lot of things, going to take a lot of work. I wanted to see how much we could do without doing any of that while touching as few tools as possible. And so I made my focus WIT bindgen and wasm time WIT bindgen to create sort of as idiomatic as possible bindings that resemble what preview 3 bindings would look like, while leaning heavily on code generation rather than component model ABI changes and WIT changes. And so I'm gonna, we can dig in later if there's time and there's interest. But I wanted to kind of start by showing a couple of examples of what this would look like from the guest perspective. So if you're familiar with cargo component or the lower level WIT bindgen generator for Rust, hopefully this will look somewhat familiar. But essentially, we're using WIT bindgen just like we normally would, telling what world we want to generate bindings for, and specifying which type we want to implement the exports for using. But we added this new ISIS-WASFA flag that essentially tells it, I don't want just normal synchronous bindings, I want asynchronous bindings to this WIT world. And what that produces gives us the ability to export an async trait or implement an async trait that exports a function that implements a function that the host can call asynchronously. And we can see here kind of a cool thing where we're now awaiting a preview 2 pollable produced via the subscribe duration function, just in the most natural way possible. Like this is as idiomatic, async Rust as you could imagine, and this is composable. I could do several of these in parallel and await all of them. You could do an outbound HTTP request and add a timeout to it, rather than kind of the rigmarole that you have to go through in preview 2, and it just works. There's no need to call the poll function. Instead, the host is your executor. So the host is going to multiplex incoming IO as necessary. So that's kind of cool. And then, of course, finally, we're doing a host call itself that's asynchronous, and the bindings kind of take care of the details of how that works behind the scenes. And now for a more complicated example, we can start to look at what a WASI preview 3 HTTP service might look like. And this kind of goes back to some of the slides that Luke started out with, in terms of like what does that elegant, beautiful, request response control flow look like, in preview 3. And this tries to essentially, this might actually be exactly what this would look like. Oh, well, no, I take that back. I'm using a record to represent requests and responses here instead of a resource. So not exactly, but in spirit, it's the same idea. And so we can look at this control flow and see a couple of things I would note. First of all, we're returning a response immediately before we've and the goal here. This is sort of an echo thing where we're basically streaming in the request body and streaming it right back out as the response body. And what we do is we actually do a spawn. This is kind of like a Tokyo spawn if you're familiar with the Rust ecosystem. But we're spawning this task so that we can return that response, which in the real component model would involve that canon task return call, but in this case we're kind of the implementation obviously differs because we don't have that yet, but the developer experience remains the same, which is we spawn this task which handles the piping of the request input to the response output, and we can return the response before that finishes, and so the piping could take as long as it needs to. And then finally, I want to point out a middleware example. So we just saw that service. Imagine that's business logic that's doing something more than just echoing. And now we can actually add some transparent middleware. And this is the composition aspect. And this works today using a very lightly modified version of wasm compose. And so this middleware is responsible for handling request body decompression and response body compression, and doing it transparently so that the business logic doesn't need to worry about it. And this for me has been sort of the holy grail of async IO composition. We're streaming both directions. And so what we do is, we basically take that request that we got from the host, we we basically replace the body stream with a pipe that we're going to do our decoding with, and then when we get and then we're going to basically call into the other component, into the business logic right here. We're going to get a response back from that, and then we're going to replace the body again with a transparently decoded, encoded compression of the body that we were given, all using streaming, all asynchronous, again using the spawn primitive.